Ireland, the land of saints and scholars. Ireland's literary heritage is well known, but in the history of mathematics too, Ireland has a role to play. For in the middle of the 19th century, discoveries were made that were to revolutionize algebra and lead to its final liberation from arithmetic. William Rowan Hamilton was born in Dublin in 1805. He was to become one of the truly great mathematicians of his time. From a very early age, he'd shown remarkable abilities. By the age of 7, he could read Greek and Latin and could recite texts of Homer in the original. At 13, he was able to perform phenomenal feats of mental arithmetic, such as calculating the prime factors of huge numbers in his head. His knowledge of advanced mathematics he acquired in his teens from the French textbooks used at the École Polytechnique, works, for example, by Legendre and Lacroix. While still a student at Trinity College, Dublin, he was discovering original results in optics. He was elected Professor of Astronomy and Royal Astronomer of Ireland before he'd even completed his undergraduate studies. He was then still only 21. At about this time, one of his great achievements was his publication of the theory of systems of rays. It's a mathematical account of the behavior of light. Such a complex mathematical description of a physical situation had rarely been seen before in Ireland or elsewhere. And about 5 years later, he published his third supplement to his essay on the theory of systems of rays, in which he predicts how a ray of light will behave when it's passed through a prism with biaxial symmetry. We won't go here into what biaxial symmetry means precisely, but the important thing is that such prisms didn't actually exist, and so Hamilton had no experimental evidence to suggest what would happen. His mathematics predicted that a ray of light striking the prism at the correct angle would form a hollow cone inside the crystal and emerge as a hollow cylinder from the opposite face. This was called internal conical refraction. If, however, light was focused to a point on the surface of the crystal, it would pass through as a single ray and emerge as a hollow cone. Hamilton called this external conical refraction. Naturally, he was keen to see if his predictions could be verified. However, it took his colleague at Trinity College, Dublin, Humphrey Lloyd, some 2 months to obtain a suitable crystal and verify that the prediction for external conical refraction was indeed correct. As a result, in optics, conical refraction is a mere curiosity. But as an example of mathematical prediction, it's a tremendous achievement, one of the greatest achievements in mathematical physics. Its importance was recognized, and Hamilton was awarded the Royal Medal of the Royal Society in 1835. And a little later that same year, he was knighted at a meeting of the British Association held in Dublin. Thus, at the age of 29, he was recognized as one of the greatest applied mathematicians of his day. At that meeting of the British Association, Hamilton presented 3 papers under the heading Theory of Conjugate Functions or Algebraic Couples, with a preliminary and elementary essay on algebra as the science of pure time. Let's look now at some of the ideas expressed in these papers, beginning with the concept of algebraic couples. Hamilton, like many others, was interested in the formal algebra derived from complex numbers. A complex number has the form a plus bi, where I is an imaginary quantity which satisfies the rule I squared equals minus 1. Complex numbers can be added. For example, 3 plus 2i plus 4 minus 1i is 3 plus 4 plus 2i minus 1i. which is equal to 7 plus 1i. They can also be multiplied. 3 plus 2i times 4 minus 1i is equal to 3 times 4 plus 3 times minus 1i plus 2i times 4 plus 2i times minus 1i. And because I squared equals minus 1, this eventually becomes 14 plus 5i. But this imaginary number I was a source of some controversy at the time. However, Hamilton, following the methods of Wessel, interpreted complex numbers as points on a plane. So 3 plus 2i could be interpreted as the point 3, 2, using a pair of coordinate axes. What Hamilton did was to dispense with any concept of imaginary square roots of minus 1 and simply consider number pairs or couples. He defined rules for adding couples. AB plus CD equaled A plus C, B plus D. And for multiplication, AB times CD equaled AC minus BD, AD plus BC. In particular, 0, 1 times 0, 1 equaled minus 1, 0. This is in fact an exact parallel to addition and multiplication of complex numbers. Hamilton avoided talking of imaginary numbers by starting with number couples and defining a set of formal rules for their addition and multiplication. The logical development was to consider number triples, or triadic fancies, as Hamilton called them. In other words, to look at number triples like A, B, C, to find rules for their addition and multiplication, Hamilton tried to extend the analogy from complex numbers. He interpreted A, B, C as A plus BI plus CJ, where both I squared and J squared equaled minus 1. Adding triples was easy. For example, 3 plus 2i plus 4j plus 1 plus 4i minus 3j equals 3 plus 1 plus 2i plus 4i plus 4j minus 3j, which gives this. But the question now is, how do you multiply triples? Multiplying these two triples as if they were complex numbers produces this extra term in ij. What is this product ij? What can ij be? Hamilton pondered this question for a long time, so much so that it seemed to become something of a family joke, as he tells us in a letter to his son Archibald, written some years later.
Every morning on my coming down to breakfast, your little brother William Edwin and yourself used to ask me, "Well, Papa, can you multiply triples?" Whereto I was obliged to reply with a shake of the head, "No, I can only add and subtract them."
Hamilton tried several methods of attack over the years. Part of his problem related to what he called the modulus of a triple. For example, the modulus of A plus BI plus CJ is just the square root of A squared plus B squared plus C squared. And he wanted the modulus of the product to be equal to the product of the moduli of the individual terms. And none of his attempts for a value of ij allowed him to achieve this. And then suddenly, one day, it was the 16th of October, 1843, he had the necessary flash of inspiration.
As I was walking with Lady Hamilton to Dublin and came up to Broom Bridge, I then and there felt the galvanic circuit of thought close. And the sparks which fell from it were the fundamental equations exactly as I have used them ever since. I pulled out on the spot a pocketbook and made an entry on which I felt that it might be worth my while to expend the labour of at least 10 or 15 years to come. But then, it is fair to say that this was because I felt a problem to have been at that moment solved, an intellectual want relieved, which had haunted me for at least 15 years before.
So excited was Hamilton that he actually scratched his formulae on the stonework of Broom Bridge. Here's what he saw in his flash of inspiration. Instead of triples, using I and j only, he added a third distinct imaginary number, which he called k, also satisfying the rule k squared equals minus 1. So he now had quadruples, a plus bi plus cj plus dk, or quaternions, as he called them. To multiply quaternions, we use I squared equals j squared equals k squared equals ijk equals minus 1, so that ij equals k, jk equals I, ki equals j. But ij doesn't equal ji. Ji equals minus k, kj equals minus I, and ik equals minus j. A good way of remembering this is as a cycle. Going clockwise round the circle, ij equals k, ki equals j, jk equals I. But going counterclockwise, ik equals minus j, ji equals minus k, and kj equals minus I. With multiplication expressed like this, Hamilton had produced a consistent algebraic system of quadruples, but one in which multiplication was not commutative. This was the first non-commutative algebra ever to be developed, and it's why we say that Hamilton freed algebra from arithmetic and opened a way for other mathematicians to re-examine the basic concepts of algebra. Hamilton was so pleased at the result that he wrote a poem in commemoration of it.
And how the one of time, of space the three, might in the chain of symbols girdled be.
Hamilton saw the four elements of a quaternion: